Okay. So welcome everyone, and nice to meet you all. And good morning, good afternoon, whichever time zone you are in. Let's start. My name is Piotr Golkiewicz. I am a customer success consultant, subject matter expert for life sciences. And today we have quite unusual webinar, which was requested by many of you, many customers. Which is devoted to structure editor. Usually we do this based on specific use cases, areas of chemistry. So I will do it for organic chemists, for inorganic chemists, material scientists. Today is pretty sort of technical focus. And by definition, because we talk about structure editor, I think it's mostly for organic chemists. This meeting is being recorded, as I said, and let's start. First of all, I want to show you a couple of slides really quick. And I will be doing this every time because we have more of this series. I already said it's structure editor, okay. We have more meetings coming. There was also a request for Reaxys predictive retrosynthesis module, which will be this Thursday at 11. I hope if you found this one, then definitely you also know about the other one. Which is also mostly for organic synthetic chemists, because this is about retrosynthesis and especially about predictive retrosynthesis. We also then have on the 2nd of, no, it's not the 2nd to 4th, it's the 2nd of April at 11, we have Reaxys Query Builder. So then we will talk about using a Query Builder, advanced search tool in Reaxys to build more complex queries. And this will be then, I will try to use examples from all different areas of chemistry and related sciences. So chemistry, biochemistry, inorganic chemistry, material science, analytical chemistry. So we will try to use different examples, physical chemistry as well. So to show how strong, what is the power of a Reaxys Query Builder. We also have, I also usually do Reaxys Open Office. So every month, roughly in the middle of the month, and if you find it, if you not, you can ask me as well, but I think it's also public. The next one is on the 15th of April at 11. This is the session where where I don't have any agenda, and I count on questions from all the participants, and we talk about your questions, your problems. We work with your examples, okay? So that's the open office, and this is happening basically every month in the middle of the month. But there is a schedule. If you want, I can share it with you. And also what we are working on as a team is a lecture series on Reaxys and Embase. And this will be also publicized. This will be on a big marker. It's a different platform, but there will be a whole big number of different sessions. It's for all the products. I'm participating in life science ones, but there will be also all the other products there. So lots of things are being arranged, and there is a lot of possibilities for you to learn and be in touch with us with Reaxys. Okay, so every time I thought I will do a couple of slides. I don't want to bore you to death. If you already have seen this, then you may go and grab a cup of coffee or a tea in the meantime. This will be very short, couple of minutes. But I noticed that every time I have different new researchers, librarians, users, participants joining us. So I thought it's always good to at least show you the minimum base introduction to Reaxys, and then we go online and then we play with the database and then we see how it works. So talking about Reaxys, it's the database with a very long heritage, starting with Ballstein and Melin, organic chemistry. Reaxys as a database was launched in 2009. Before it was a Crossfire Ballstein. And since then, we are first of all adding a lot of content and also adding a lot of functionalities. Functionalities like new user interface in 2016, new Reaxys medicinal chemistry module, which is now called Reaxys Targets and Bioactivities, which is, to my knowledge, the biggest available database of biological activity. In 2020, we added Reaxys commercial substances. This is a database of commercial suppliers who collaborate with us, and basically in Reaxys, without leaving it, you can check what's the availability of different reagents, chemicals. In 2021, we started a patent expansion project, and this is a huge project devoted to improving our coverage of patents. Now we are covering 105 patent offices and 170 patent classes, so we can say patent coverage now is really good. It's enough to say that we grew from 2 million patents to 45 million patents in 3 years, basically. 2021, we have included predictive retrosynthesis module. This will be covered in the next session. And this is artificial intelligence-based synthetic prediction tool. We started with pending AI, one engine from Professor Mark Waller, famous person in terms of using of artificial intelligence to predict chemical reactions. Now we also have ICTOS, the second engine, so we have 2 engines to choose from. So that's how Reaxys is developing, and I think it's not the end. We are still working on new tools, new ideas. We are also adding a lot of content, like extracting, for example, substances reactions from patents, which is a completely big new project because that's a lot of documents. Very quickly, the core philosophy of Reaxys and how it is different from other databases. Reaxys will try to answer your question as quick as possible. And this is thanks to extracted content. We extract a lot of information, structures, reactions, properties, reaction conditions, all the physicochemical properties, bioactivities, use of the product, isolation from natural source. Whatever we can extract will be extracted, and you can look at data before you have to go to the original document. And every time, of course, there is a link to original document so that you can check the article or a patent. The interface, I think we will be there in a second, so we will see, but that's, I think, pretty nice and clean, and yeah. This is, of course, the personal preference, but I think it's nice, better than other databases. When you retrieve information in Reaxys, especially in quick search, it will try to build an algorithm for you, so then it will help you to ask the question. Of course, if you use the structure editor that we will be doing today, then, of course, it's not happening because the database knows you are searching for a structure. If you search for something that is not obvious, then you will get the choice. Also in a query builder, that will be the subject of the second meeting. The database will know what you want to do, which fields to use, so it will not give you these options. I mentioned extracted information. There's a lot of it, just to give you an idea of bioactivity, physicochemical properties, spectral information, other data, a lot of information. And this is all extracted and always supported by the link to original document. So just to summarize quickly and give you an idea, Reaxys is not any longer, I think it was, actually it never was, but it's not what people think. It's a organic reaction database. It was never that, but today it's even more not that. I would call it life science database at the moment. First of all, it's a bibliographic database with more than 120, I think, at the moment, million records, covering 18,000 journals, substance properties with close to 300 million substances, and growing very, very quick. We get new sources as well of data, of structures, among those patents, for example, collaboration with big companies as well, and we get their libraries as well. Property database, this is more than 500 million experimental properties and growing. I think it's much more by now. And this is distributed in 500 fields that we use to search, and this will be useful when we talk about query builder in the one of the next meetings. Chemical reaction database, of course, over almost 70 million reactions, including reaction conditions, including experimental procedures. On the left, we see bioactivity database. This is Reaxys targets and bioactivities. more than 48 million experimental bioactivity data points and target database. Then on the right, patent database, as I said, 105 patent offices, 170 patent classes, 45 million patents, and predictive retrosynthesis model. This is Reaxys, and this is what it can do for you. So this was a quick demo, quick introduction, and I think we don't have enough time. We have only 1 hour, so we don't have more time to go into details. But if you are interested, let me know. You can ask the question, use the chat. I will show you my email again at the end of the session, so you can ask me the question, and please do not hesitate to do so. That's my job to make sure you are successfully using Reaxys and you are happy with it. Okay, so this is Reaxys Quick Search, and basically our interest today is structure editor. So draw, right? I will skip completely other parts of searching. Today we are only looking at structure editor, okay? So to start with, we have 2 structure editors, and if you don't notice, we have Marvin.js and Chemdraw.js. JS means JavaScript, means the internet version. It's simply it's simplified. It's less functionalities than the desktop versions, of course. But if you want, and if you like Chemdraw, for example, interface, I think this will be familiar to you, right? I prefer Marvin, and today we are staying in Marvin.js. Basically, what you can also do, you don't have to draw everything. You can import files. You can copy from other databases. The easiest way is to copy smiles, because otherwise you might be copying the content. Oh, I see Katarzyna raised the hand. Please ask the question in the chat, ideally, if you can, if there is a question, okay? Please use chat, and I hope it works. And if chat wouldn't work, there is also Q&A. So Katarzyna, please use the chat for a question, okay? I will be monitoring this. Thanks. And please ask questions, and of course, let's talk. We don't have too much time because I have prepared many examples, but we try to be in time, and we also I would be really happy to answer your questions. I want you to be sure that okay. I ask later. Okay, good. You can also write me an email, and even in Polish. I see you are from Poland, so good. Okay, so as I said, two structure editors, copy, paste from other structure editors, no problem. And ideally smiles to get rid of formatting. You can also open files of different formats. So there's also quite different possibilities to do this. You can search for a structure, you can search for as drawn, you can search for substructure, meaning any substitution on any atom. You can also search for similar compounds. So I think this is quite normal. Also, here on the right, you see you can search for tautomers, stereoisomers, additional enclosures, related Markov structures, salts, mixtures, isotopes, charges, and radicals. So there is quite a lot of these options, and you can switch on and off those that you want and don't want. And you can also set up your preferred default setup. But for this to do, you need to be logged in. You see, I am logged in here, and this would be my general recommendation. You can work, of course, as anonymous user. If your institution has Reaxys, then you can work within the IP range of the university, or even remotely if you have remote access. For example, via library, a VPN or proxy server. But to log in with your own personal profile allows you to do many things. You can, first of all, change the interface. You can, for example, set up what you want to have as a default. You can save queries, export queries, save lists. I mean, you can do much more. You can do email alerts. So there is a lot of things you can do when you are logged in user. So I strongly recommend to do this. And also your session lasts longer, by the way. If you are not logged in, anonymous user, your session may expire after half an hour, then you have to start again. So it's not very good. Good, coming back to structure editor, we know what we can do here. And yeah, before we even start drawing, I think there is a really good option here, insert structure from name. So for generic names, drug names, maybe not the UPAC names, because this option doesn't have this auto correct option that you have normally in other fields. Even if you do it in a quick search, if you start typing, Reaxys will try to help you to suggest entries. In the case of the UPAC name, for example, it would be UPAC name. But here, CAS number, chemical name, inchi key smiles, whatever you can enter. Even the name of the drug doesn't matter. And Reaxys will know this and it will draw it for you. So this is very easy. You don't need to draw everything, especially if you have big scaffoldings and you have the nearest one. You can import it directly in here and continue drawing. So this would be the first option, insert structure from name, and this speeds up work quite a lot. Of course, drawing structures, I think it's quite obvious, and we don't need too much of the knowledge. Let's do very quickly structure just to have something here. Nope, it's not what I wanted. And yeah, here we have benzene sulfonamide, right? And very simple. So this is nothing special about it, and every structure editor could do this. If you want to search, you just do transfer to query. Then we have it in a query, and we do the search, right? View results, and we are in a record of a structure, and we have all the data. I will not have time today to describe you all these details, but you quickly notice that you can get the right likeness by activity data, physicochemical properties, spectra, all the other data, and also preparations, reactions, targets, and documents. So this is quite obvious, right? So this was searching for a structure. One question I received recently, can I also search for inorganic compounds? Yeah, you could, but this tool was actually was mostly created for organic compounds. Drawing an inorganic compound, especially if it's usually ionized, it's not very easy. We could try, why not? We could try like this. Let's see if this will work. Okay, so you see, this is looking like this, but no problem. We can even run this search, and I think it should find the substance. So, but this is not my favorite, honestly. I mean, that's not the best way to look for inorganic compounds. I will talk about Query Builder in a meeting next week, and then I show you molecular formula, which is much easier and quicker, and in my opinion, more reliable for inorganic compounds. Okay, substructure search. How can we do the substructure search? Let's do the imidazopyrazine. Maybe something quick. Okay, I use quite easy examples, but then we get more complex maybe later. But basically, very quickly, we search for substructures, right? And how can we do this? Of course, the first option would be substructure search, meaning any substitution on an atom, uncontrolled. I think I don't need to show it. We get thousands, 5.6 thousand compounds, quite obvious, right? This is quite a big group of compounds. This is a little bit too generic. Just to show you, Reaxys will show you in blue. When you zoom in, it will show you in blue your searched scaffolding. So you see where it sits in your structure. So that's quite easy. So generic substructure search, this is a little bit maybe too generic and too much. And what we could do, before we go to specific substructures, we could look at a couple of things, like, for example, maybe we could lock specific atoms, right? So we say like negative selection, and locking atoms is here on the left side. Maybe I say I don't want substitutions on these two, maybe on those nitrogens, right? I want only substitutions on this side of the structure, but and I still use the substructure search, right? So this is like a negative selection. I say everything except those, and you see the number of structures is less, 890 structures, and they will only have substitution on this, on the right side of my structure here, nothing on the left. So makes sense. You could actually do the same you can lock atoms also. If, let me unlock them first. You can do exactly the same if you would do the hydrogens, right? So if we would add the hydrogen, like, oops, sorry, that was not what I wanted. Okay, implicit hydrogens. This is what we can also do to lock the atoms. This is exactly the same like lock the atoms. We could also add all hydrogens in this case like this, right? So we could also do hydrogens like this. So depending how you want this explicit and implicit hydrogens. So this is like searching for a generic structure or substructures and then trying to limit the number of substitutions and limit certain atoms, lock certain atoms. This could be one of the ways of searching. But I think much better substitution is when we try to be more specific. So that means we are not searching as a substructure, we search as drawn, but we try to specify where do we want specific substitutions. Here we can do many different things. We could be quite specific, like I want, I don't know, chlorine, for example, chlorine on a specific atom, why not? We could be more generic. We could say it could be any halogen, right? And yeah, that could be any halogen, for example. We could say also any group. Here, when you see on the right, this orange R, we have Reaxys generics, and then we have acyclic, cyclic groups, all different types of groups. And here on the bottom, we also have any group of or hydrogen, etc. So I could say, yeah, I want here any group, for example. We could also do, because I showed you just one atom, but I think quite a nice feature is atom lists as well. So when you click on atom list and then you say, for example, oxygen or sulfur, you see on the tip of my cursor, both of those are here. And I could say like this, right? So in one search, I will search both for oxygen and sulfur. And I could even go and go on and say, and I want then any group to be attached here. I could be more specific as well if I wanted any cyclic group and a cyclic group and any heteroaryl, for example. So it's up to you how you want to do this. So you see many different options. You can also do any atom, if this is not a group, but the atom, any heteroatom, any metal as well, especially for coordinated compounds. This could be also one way to search, not for specific metal, but maybe any metal. So these are all these ways. There is also one more way of searching for generic groups, which is abbreviated groups. Abbreviated groups, you just start typing, and then basically you can select the group, and you can try to substitute it, and you see when you right click, you can expand, and right click, you can contract. So that's another way to speed up your search. You don't need to put everything here. If this is phenyl, it should also be easy to do. And also, rather than drawing and expand and contract. This is not a big thing, and I think that's quite easy, but you can also use this. So this is also quite handy. Okay, let's go back to our initial structure so that we start again drawing something on it. What I wanted to show you also is different types of bonds, of course. And this is here. You see this small black triangle. There will be more options: single, double, triple, and so on. Single or double, up and down, cis trans. This is a coordinated bond, and this is, for example, quite useful, in my opinion, position variation bond, so that you can also mark certain atoms for substitution, like, for example, these two. And you can also use If you want to mark more of them, then ideally you should use the selection tool, and you could do with shift as well, like this one. So they don't have to be in one place, and then you can click on position variation bond. So you can get this, meaning this, or this atom, and this is by default substituted with the methyl group, but then you can put here anything from, for example, alkyl. So there will be only those compounds that have any alkyl on any of those three atoms. So that's a very, in my opinion, useful option. If there are any questions, again, please, I will remind you from time to time, I'm open for questions. And if you want me to stop somewhere or expand on something, I'm aware of time. So I'm trying to cover many more examples, but if you have any questions, please ask. The next thing I wanted to show you, okay, it's a repeating unit. That's also very, very useful. Let's have, again, very simple structures, maybe some atom just to have it nice. What we want to, that's 2-methyl and aziridine, and we want to search for compounds, first of all, that have a different length of the chain here rather than the methyl. So we would use this repeating unit option, mark this atom and say, I don't know, 1 to 5. I mean, we can do exact number or we can do the range. This means we will have from 1 to 5 carbons in a chain in our search. We don't have to run separate searches for different length of the chain. We can do the same in a ring, by the way. So if we want, we started from like three membered ring, but we won't go up, for example, to, I don't know, 6-membered rings, right? So how do we do this? We do the same. We just do the repeating unit, and we repeat atoms. So we say 1, 2, 3. If this is 1, then of course we stay with 3 carbons in the ring. But if it will be 3, it will be altogether 5 atoms, right? Because we have 2 and 3, there will be 5. So like isopentane based compounds. So you see, we can test different ideas and build groups of atoms in a different way. And maybe we should try to run this search just to see how this works. 217 compounds, okay. So you will see different sizes of the rings, up to 5, but we also have 4, we have 3, right? And we also see different lengths of the chain here, which is connected. So one search, many results. So don't go and check each of them separately. Try to build searches which give you an idea about whole space, compound space, and all of them at the same time. Okay, what else? Maximum substitution. Yeah, this would be another way. Okay, maybe let's clean it again. Let's maybe try to. Okay, that's my easy example, right? I want this. I think it's better than very complex examples at this stage because this is quite transparent. What we can also do here, as shown, but we could do the substructure search if we want to test substructures, but on more than one atom specifically. Then we could also do S-max, so maximum substitutions. So even though we have S drawn, we say we want the maximum substitution on these 2 carbons, this will show us the compounds that will have substitutions here on these 2 compounds. So we could use the G, like generic groups as well, or we could use the maximum substitutions, and this will explore all the options of these 2, right? I think the way to do it with the generic group would be to do any group or hydrogen, because there's also an option where there is only one of those which is substituted. So I think the option to this, I think would be any group air or hydrogen, and this is the same result, I guess, because then it could be empty or it could be both, or even no. Oh, we have a question. Reaxys region close to chemdraw could be used to structure from the raw data and from the different spectrum to know the class of compounds. Yeah, okay, so there are a couple of questions here. I think one is if Reaxys is close to chemdraw, maybe you were not in the beginning of the presentation. I was showing that we can actually use chemdraw here, which is a JavaScript version. So you have chemdraw JS is one of the editors. So that's one possibility. Of course, if you use chemdraw, for example, desktop version, then you can copy smiles and paste it here as well very easily. And chemdraw, I think starting from version 18, it has even a Reaxys button. So you can just press on R when you draw, you can draw, and it will import Reaxys and will immediately run the search automatically. So you don't need to do anything. So chemdraw is, yeah, we also try to give you this by the simple version, or you can copy paste, or you can bring it import directly from chemdraw. The question was also about yeah, from Spectra. No, from Spectra, I think not, because you need to draw it anyway, but you can import if you have a Spectra database and you find a compound, copy smiles, and you can bring it here very easily. And I think there is also the last part of the question is about class of compounds, the basic core of our structure. Yes, this is exactly what we are talking about. I'm talking about substructures, right? And these substructures you can find as a substructure, meaning basically you don't control a substitution. And if I wanted to, let's maybe do this, right? And maybe I show it once again quickly. Then we don't control the substitution. So it's 5.6 thousand compounds that have substitution on any of those atoms. So all the compounds that have a specific scaffolding, specific generic group that you want to have, and then you see all these compounds. I will show next week when I talk about the query builder, I will show how to use structure editor together with other fields. So we will be able to search, because 5.6 thousand compounds is a lot, but we will be able to search for compounds having this specific substructure, but at the same time being bioactive on specific pharmacological target, compounds that maybe can be used for a specific use, compounds that are isolated from a natural source. So there will be many, many different possibilities to match this with other ways of asking. So yes, absolutely, we are now talking exactly about this searching for substructures, and I showed a couple of ways. So doing a substructure and trying to log the atoms, that means exclude them from this substitution, which is this button, log atom, and you just log them, and this would be substructure search without those two locations. Or or you can search as drawn, but then we try to substitute something, and for example, any alkyl here on this position, and this means there will be no substitutions on those positions, only on this one. So you can be very, very specific in how you want to search. You can use different types of bonds. You can use, as I said, repeating groups. So all these different tools that can help you in looking for data. On top of this, you can edit the atoms. So if you right click on the atom and you say atom properties, you see all the details about the atom, right? So this is carbon, this is no charge, so you can enter the charge here, or if you want the radical, monovalent, divalent. You can also go to advanced, and here, for example, you can do the substitutions. So you can do as drawn or exactly, and you can enter the number of substitutions, and so on. And here, I think you could also, isotope is here. You have to just unlock the field and you can use the isotope as well. If you wanted C13, just type 13, and this will be the isotope here as well. So quite easy to manage the atoms. And the same for the bonds. Right click on the bond properties as well. You have single, double, triple, you can change it here. Topology in ring in a chain. I think I will show it somewhere. Or maybe let's show it here, but not, let's use just this. So if I'm, okay, and maybe go from this isotope, we don't need this. What if I just delete it? It will be easier, I guess. Okay, we log the thing. Okay. So if I'm looking for substructures, this is also quite nice. If we look for substructures now, it may happen that we will have rings closed here on these two bonds as well. Maybe let's, sorry, we need to search for substructures, of course, not the structure, substructure. You will see in my results that we will have also, I hope I can find it in the first pages. No. Like this one. You see, we have, no, it's not this one, not this one. Sometimes you will see the rings closed on our, okay, this is not a big problem here, at least in these results, but quite often I find this. So what we can do here is we also can change the topology of this. Right click, bond properties, and go in chain. In this case, you are making sure there is no ring closing here on this atom. Oh, is there a question again? Thank you. Okay, good, good. I hope I answered. Please feel free to ask anytime. So you see, a chain prevents us from blocking um, um, the ring here as well. Or if you want the ring, then you basically say the ring, and maybe that's the opposite. I couldn't find any ring closed here, but let's try now. Maybe this will be better. Yeah, here like this. Okay, we can see that here. Great. So that's quite transparent and easy, I guess, that we can do this quite easily. We also have a reacting center, so we can also do like make or break or reaction center or change. I think make or break. I will use this in one of my examples later. Make or break. You will see how this works. Okay. Reactions. I think that's quite easy as well. Let's use my other compound that I was using. Whatever. Okay. We just repeat again. Repeat this carbon, so we have a chain. We repeat this carbon, 1, 2, or maybe why not up to 6 atom, up to iso. Yeah, 6 atoms of carbon and reactions. I think that's quite obvious, right? The arrow. And we can also put above the arrow the reagent or a catalyst if we want. And maybe we can, for example, see the reactions in potassium carbonate. Okay, and look what will happen if I will put it too closely. And this is what I've done recently, and I was thinking what happens. So, okay, and we do this as drawn, because we have a substructure coded basically in these repetitions. And I've done this recently, and let's see, one reaction. Okay, that's absolutely not correct. And this is basically my fault. And my fault is that I have put this too close. Okay, so I wonder if I can now. Okay, now it won't let me even to do this. Okay, let me. I have to do it once again. So what I've done is I put this too close, and my arrow was basically short, and I was hurrying. So make sure this is not overlapping with your starting material. Basically, this would be my suggestion. And hope now we can get, yeah, 1,000 reactions. That's much better, right? From 1 to 1,000. So obviously the first answer was not correct. And here we will see potassium carbonate in reaction conditions. As I mentioned, you also get experimental procedures wherever possible. So putting the reagent or catalyst above the arrow is nice. You can also put the product if you want, or a group of products. What you cannot do, you cannot put the solvent. And to put the solvent, you will need to use Query Builder and use the specific fields for a solvent. I will show this next week. So reagent or catalyst works fine. The next thing I wanted to talk about is atom mapping, which is here, which is also quite nice. You can use this in many cases. The two cases that I think are the most important are the change of functional group, or like when you have more than one group that you want to do something, like protective groups, for example. First, very easy example that I always show. Maybe there are more, because there are more. I just clicked on 2D just to have it straight. Control C, Control V. Copied that, and what I will want to do, I will want to change this carboxyl group into 3-fluoromethyl. I need the arrow, of course, and that would be my reaction where I have my starting material, my product as drawn. Quite easy. I can be okay with stereo, additional enclosures, maybe not. Salts, okay, mixtures. I don't want radicals. Charges, maybe, why not? Okay. Transfer to query, just searching for as is. So I'm getting two reactions, two examples, and that's absolutely okay. The transformation of the functional group is beautiful. If I will go for substructure, and this is the moment when we want really to discover the whole group of reactions, having the specific transformation, but at the same time see those with bigger or different scaffoldings, extended scaffoldings. So I'm allowing substitution basically on any atom, including my groups in the atoms in the functional group. Let's see that. And this is not preventing us from 1.8 thousand reactions. And what we will see is that, for example, here my 3-fluoromethyl is already present on my starting material. Or like here, my carboxyl group is ethylated, is substituted. So that's not what I want. I want a clear transformation. How do I do this? Among those reactions, somewhere, there must be those, oh, like this one. You see, this is nice. This is what I wanted, the clear transformation. All the other atoms groups are not changed. So basically, this is only here where reaction takes place. So this is nice and clear. But how to find these reactions among those thousands or 1.8 thousand reactions? Very quick and very easy. We come back to our editor and we do one more thing. We can use this field, at least in Marvin, which is called manual mapping, or basically in any editor, you can use the same tool that you use for drawing reactions. So plus or the arrow, right? This is how it works, but it also has the third function. If you start on this carbon and drag to this carbon, you see we mapped this carbon atom, it's one. We could add more, and we will do this in a second example as well. So that's quite easy. Now I change nothing more, transfer to query. I still am looking for substructures, and you will see 27 reactions. So among these 1.8 thousand, there are 27 that I'm interested in. Quite nice and clean, okay? The second example could be like protective groups. Here we could have like, and this is another example which is also based on substructures. So I'm looking for, this will be like EOC. Okay, so this is one. And maybe just to make sure we are in sync, I will just, okay, we have hydrogens here, but just to make sure, I will put implicit hydrogens. And then the second one would be, again, I see again, and here it stays. So there will be two, but only this one on the phenyl will be detached, and the other one I want to stay. And we need maybe like this, so at least minimum the structure. So now what I will do is I will first of all use the same tool, and I will map this nitrogen and this nitrogen. But you see, this is marked with 1 and this is marked with 2. So these are two different nitrogens. What I will also do is I will do the substructure search. So I want the compounds that have both of these groups somewhere, and this reaction coming alive, and this protective group being detached, and this one staying. What I also want to do is to click on more options. And in the latest version, I already have this option, which is quite useful, keep fragments. This is by default both separate and together, right? But make sure it's together, meaning we will see the structures where they are in one compound. Of course, what we also need is the arrow, right? Yeah, I would forget this. So we want to see the compounds where both of them are on one compound. We don't want to have separate ones. If you are looking for separate ones, then of course you click here and you leave the separate, but I want together. Okay, you can even do it like this. So this is then my ready drawing. And then we look at, oops, I done something wrong like this. What is my mistake? There must be, maybe I'll just look and this as is. Because this is, okay, let's do it like this. No, come on. This is, and I have my substructure, and I have my nitrogens, maybe the hydrogens. Okay, let's switch off the hydrogens. Let's look now. That's strange. Okay, okay, so maybe I locked the hydrogens unnecessarily, so this should be, I didn't allow the substitutions in this case. It's okay, this was stupid. But okay, you see now my BOC groups here and only one remaining on my product. So that's exactly the idea of this reaction. Okay, the next thing I want to show you is smart groups. Okay, we have to speed up. It's only 12 minutes. Oh my God. Smart groups, this is also a beautiful option if you want to search for a space, like product space, a compound space. This is a nice way to do this. I do this on purpose in a corner because I will need this space, but maybe I did it too much in a corner. So I hope you can see it. Maybe we can move it a little bit. So that would be my scaffolding. I need an oxygen here, and I want to have this atom repeated. Again, I'm looking for different length chains to move this a little bit farther from the rings. And now what I'm doing is I'm taking the R tool, the smart R group, and basically just dragging and drawing R1, R2. You see, this is automatic. I do nothing else but just drag and draw things. Very easy. I could click on any of those groups in the meantime, switch off auto numbering if I wanted R3, 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 R3. But I also can change this afterwards, because I do want both from the same class of ligands. And then what I need to do is I need just to say what are my R1, R2s, R3s. Let's do a couple of simple examples. This will be maybe not all I would be thinking of, but just couple of. This would be the R1. R2 could be any halogen or this is connected by oxygen. Okay, and R3, I will allow hydrogen because I want maybe only one of those or none. Why not? Then any alkyl, I'm just typing alkyl or any aryl. I could go to generic groups and do it, but I can do it like this much quicker. And then I again use the smart R group, that the one I was just doing the groups, and mark like this, very easy, just drag and mark. You see, I do nothing more, just drag and they are automatically marked in groups. Yeah, the last thing I might want to do, and I think I have to do, is to show the connection in the more complex groups, attachment point, which is the next tool here in Marvin. So basically showing what is the attachment point, and for the others, I don't need to do it. And I do as drawn because I don't want any other substitutions, only those, and this is, I think, quite enough. So I think we are ready to go and transfer to query. And we are ready to search for results. 1,000 compounds. So you see, I coded the whole product, substance strategy, and gefitinib is one of the products. And this was basically the reason why this search was done, and to search for similar ones and to study and to see what would be the library of products that we could use later, for example, for SAR studies, etc., etc. So you can code it in one search, and then you can go into by activities, which is not a subject for today, and try to find a common theme and try to see which groups are actually adding a specific type of bioactivity to the compounds. So this could be another way of looking at compounds. Okay, I was recently also asked about coordinating compounds, and I think that's also quite easy. You can use a coordinating bonds. We were recently looking for 5 or 6 member heterocycles containing either nitrogen, sulfur, or oxygen, coordinated with pallad or platinum. How does it sound? Quite complex, right? So we are looking at 5 or 6 membered compounds containing either nitrogen, sulfur, or oxygen, coordinated by platinum or palladium. So how about that? How can we do this? And I think we already use this quite a lot. So this is already sort of summarizing what we were doing. So I think I would start with a 5-membered ring. And I'm not limiting myself to aromatic compounds or iso type of compounds. So I would maybe use any bond, or at least single or double, I think, just to make sure that I have both. So this would be single or double. And I also want 5 or 6 membered rings. So maybe what I need to do is I need to repeat one atom. If I repeat one of them, and I have this option, you remember, repeating unit, I will repeat one of them. I will say 1 or 2. That means it can be 1 in this place, so then it's 5 together, or it's 2, then it's 6, right? Isopentanol, isohexane, depending on what I want. If this is not aromatic, or if this is aromatic, then of course it's like up to benzene ring. Okay, then we need at least one atom of nitrogen, sulfur, or oxygen. We could do these 3 searches separately, but remember we can do this in one search. So I'm using periodic table, atom list, nitrogen, oxygen, or sulfur. Okay, you see this is on the tip of my cursor, and I edit, for example, here. It doesn't matter where, right? Because this is basically symmetrical, or it doesn't matter the position at this stage. And this will be coordinated by palladium or platinum. So I will just switch off atom list, switch it on again, and palladium, platinum again. Okay, put it somewhere here. Then I will find a coordinating bond and do it like this, right? Very easy. So in one search, I've done so many other things and so many searches. And this is just to show you that you can code very quickly quite big groups of compounds. And of course, my examples are pretty trivial, but in more complex examples, you will know how to do this as well. And maybe to close and to try to use as many different tools as possible and maybe to have a reaction. Um, um, Fisher-Indol synthesis. Again, quite simple example I have. And this will be like this. And by the way, you see when I scroll over and I have a single bond selected, and this bond is going down and I want to change it, it's enough to press shift. You see, when I press shift, it's going up or down. So it's I could just draw it like this and force it, but you can also, I clicked shift too many times. I could just click shift and click the cursor of the mouse. So it's the same. So this will be this. We will not repeat it. Okay, we'll draw it again. So that would be my starting material. And of course, we will search for substructures. Again, we want to again look for the whole group of compounds. And we want, again, this phenyl to stay. And then we want to close the ring. Okay, and this nitrogen stays. This carbon stays. And then we try to close the ring. So the ring closes here. So what I will do is I will use right click on this and say bond properties and reaction center, make or break. I want this to be made, right? If this was to be broken, then I would, if this was a opposite reverse, then I would do this on my starting material. I would show Reaxys where to break. But in this case, I want to show it where to make the bond. And then I want here as well the let's put this like this. I said button, and we can spread we can just test different sizes of the rings, maybe up to isooctane. So let's maybe say for this should be a cycloheptane actually, because it will be 4 and 3, so it's 7. Okay, why not? And we also want to test different substitutions on this atom. What I will do here is the position variation bond on those 4. And here I want to have maybe a smart group. So you see, I'm really using all the different options and trying to see how this will work. And this could be maybe not the halogen, maybe let's be a little bit more selective. So I'll take atom list, just the 3 first halogens. This could be any no. This could be any, okay, heteroaryl, why not? And this could be also oxygen here. And here maybe we could go for an amine or OH. So again, atom list. Okay, and I need to show the connection point here. Come on. Okay, basically I'm done. Now I need to group them. Okay, so I used all different options that we learned today, and this will be my reaction, and I think I'm ready to go. Let's see, 47 reactions, very nice. So let's see if we see the indole here. We see nothing. Okay, that's okay. We see something. Good. Yeah, you see the ring is nicely closed, and we have also other substitutions here on this atom as well. Okay, I haven't limited this. I thought it would be the hydroxyl group, but it could be also substituted. Why nice? Why not? So it gives me new ideas as well. So you see, I used all my different tools and try to create drawing that would give me all different options in one picture. I have done so much work. I could, of course, save it then, most probably, because it took me so much time. I'm using this default MRV format, but you can use any other format. Basically, what it does, it saves this as a small MRV file. So you can save it, you can send it to your colleague, and when you get it or when you want to retrieve it, you just choose your file, downloads, it's here, open, and it's back here. So it's very easy. You can save those as well. Okay, I think we are 1 minute past time. Maybe we can stay 2 or 3 more minutes. If you have any questions, please let me know. Maybe what I will do, I will switch off the recording so that you are not ashamed or stop recording.